this estimate. I'm still planning to do that. I haven't done that yet, but I would say that it's much higher. It's probably 90, maybe more % of energy is due to the first mode of vibrations. Therefore, we can make our complicated life, which is hard regardless, a little bit easier if we'll consider only the first mode of vibrations. And by the way, you'll see here that finite element indirectly, maybe even directly, confirmed what I have just said. The developed simple and physically meaningful predictive analytical models enable one to determine the role of various structural materials and loading factors that affect the printed circuit board response. The analytical and finite element analyses predicted that they were in good agreement, and therefore we can use with certainty, with confidence, the analytical solutions that are much simpler, and you can obtain by using a simple calculator. With these formulas, you can obtain the result within 15 minutes, half an hour, while with finite elements, you'll be wrestling for probably several days for the same problem. In the case of practical drop heights, it is imperative to account for nonlinear effects, and the developed models can be helpful in the analysis of the behavior and physical design of printed circuit board structures experiencing dynamic loading, both in the actual and test conditions. And here I will go very step by step about numerical example. And you'll see how realistic all these things are. The drop height was 1.273 meters. It was the actual Intel test vehicle. And Milena and I got a green light from Intel to talk about that. The PCB size is 300 by 300 millimeters. That means half is 150. The thickness is 1.5 millimeters. Young's modulus of the PCB materials, Poisson's ratio of the PCB material, distributed mass. By the way, let me tell you this. Young's modulus is very important, and we want to measure it, and we want to know exactly what the Young modulus is. Poisson's ratio, as a rule, has a very, very small little effect. It's, again, as I said, it's better to be approximately right than precisely wrong. But approximately, if you put for these things 0.3, or even maybe 28, something like that. In general, for PCB reinforced by glass, has a lot of metallizations, probably 0.3 is fine. Metals have something between 0.3 and 0.35. Polymeric materials, if it's not a PCB, have something around 0.4. Silicone gels and water have non-compressible materials have a Poisson ratio close to 0.5. On the other extreme is silica glass. Its Poisson ratio is about 0.2, and for silicon it's 0.24, so it gives you a flavor about. And if you make, first of all, it doesn't change in very large ranges, but at the same time, whatever you accept would be acceptable. Now here's distributed mass of each of the 4 concentrated masses. We had 4 concentrated masses. Allocations of the 4 concentrated masses was 50 millimeters. We calculated the initial velocity, that's where it is, flexural rigidity of the printed circuit board, total mass of the printed circuit board itself, total mass of the 4 concentrated masses, the total mass of the entire system, and we calculated also the general mass of the system, because if you remember, based on that approach, it's a 1/4, 25% of the actual mass. Then we calculated the linear frequency of the bare, heavy printed circuit board. What we call bare, that we don't have concentrated masses, but we call it heavy when the concentrated masses are spread out around the board surface, and therefore yes, the board doesn't carry concentrated masses, but its weight was increased based on these concentrated masses that we call it's bare because it doesn't have concentrated masses, but the heavy because the masses were distributed. And we calculated the frequency 209.3, and finite element says 209.4. Linear amplitude, and you remember how we calculated that, was 38.69, and finite element predicts 38.1. It's good agreement with finite element, but what I want to emphasize, this number is absolutely, it's what would have happened if the response would be linear. And it's huge, because at 38.8 millimeters, imagine, it's something like that. Of course, no board will be able to withstand that, but it's a linear amplitude, hypothetical amplitude. What would have happened if we wouldn't have reactive forces? And the finite element confirmed what we confirmed analytically. Yes, it would be very close. Maximum linear acceleration, we calculated that, 173 Gs. Parameter of nonlinearity for a bare heavy PCB is huge, whatever it is. Then we calculated the linear frequency and also theory versus finite element analysis. And by the way, what you see here on the plot is a very, very useful and important result. You can see we overlapped here my analytical prediction that I derived with the finite element prediction, and these both curves are precisely the same. And what is important, that's what I'm saying here, only mode 1 was used wasn't using computation in this case and in my case, but for the mode 1 we have very good agreement. Later on you will see what happened when more than mode 1 was used by finite element. I certainly didn't use. By the way, let me tell you this: to apply nonlinear analysis, the type that I applied, even it was a challenge to solve a problem for the first mode of vibrations. I know sort of how to do that, but it's a tremendous challenge, and I don't think it's worthwhile to undertake it, how to predict the nonlinear, the role of high modes of vibration. Certainly that will bring the situation to this chaos, nonlinear chaos, which we are not in this business, and we are not very much interested in to promote the science in direction that is not practical in electronics. So you can see this excellent agreement in the prediction of the linear theory here and there. The peak amplitude is also very nice, and maximum acceleration. So from right and left, you see this comparison of a linear theory only, linear versus finite element, excellent agreement. Let's go further, and we calculated the printed circuit board nonlinear amplitude for a bare, but not heavy. It's just light without spread out masses. So dimensionless parameter of nonlinearity for the bare PCB was this one. Of course, much lower than for a heavy board. Factor of nonlinear amplitude was 0.2. So what it means? It means that nonlinear amplitude was only 21% of the linear amplitude, and the nonlinear amplitude was 8.36 millimeters, and while the linear was huge, if you remember, it was 38.7, but 8.36 was realistic, of course, and finite element prediction was pretty much the same. So now in terms of frequencies, and here it's important, and I want to discuss it and pay your attention to that. Parameter of nonlinear frequency. You remember I said that the nonlinear frequency can be obtained a square root of linear frequency squared plus mu, which is parameter of nonlinearity, A squared, and A is nonlinear frequency. If you'll do that, if you'll substitute that, you'll see that the nonlinear frequency is 6,197, when the linear frequency is only 209. The difference is significant. The maximum nonlinear acceleration, deceleration, here's where it is, and that's it's 32,000 Gs. And here just modulus of the elliptic function, that's something parameter that I needed, but the nonlinear frequency is 6,161. You see, there is a parameter of nonlinear frequency which is, it's not the frequency itself, but it's sort of close, the same order of magnitude. But it's not the frequency itself, and there is a physics behind it. I will not discuss it now. However, I'll be happy to answer questions, if any. But the nonlinear frequency, the frequency itself is 6,161. If you'll compare the nonlinear frequency with the parameter of nonlinear frequency, they're very close. And therefore, but they are both significantly higher than the linear frequency. No wonder then the maximum acceleration, nonlinear accelerations are significantly higher as well. Now the bare board nonlinear analysis. And here is parameter of nonlinearity, we calculated, dimensional parameter of nonlinearity, the factor of nonlinear amplitude, we saw it, you see it. Nonlinear amplitude, in this case, is 6.78. Parameter of nonlinear frequency is 1,600 and so on. But in this case, there is a substantial difference between the parameter of nonlinear frequency and the nonlinear frequency itself. Of course, not by order of magnitude at all, just by 20% or something. Its parameter is 1684, and frequency itself is 1446. But the period of vibrations is, a nonlinear period, is very, very small compared to the linear period. No wonder, because the frequency is much higher. And this is a very important result that I'm very happy with and want to share my happiness with you. It is bare board, nonlinear analysis, analytical versus finite element. In finite element, Dr. Vujošević considered the higher modes of vibrations. And these higher modes manifested themselves because you don't see nice sine-like, cosine-like curves. You see some impact of the higher modes of vibrations where you see just deviations from nice and smooth cosine or sine curve. But in general, if you'll consider the analytical nonlinear result for the vibrations and we'll compare that with the finite element, it's excellent agreement, which indirectly also indicates that it's okay. You can get away, as I mentioned to you several minutes ago, you can get away without considering high modes of vibration, which is good news. And now the analytical data for its linear was 6.78. Finite element in this case was 7.78. Now with concentrated masses. So we also did all these calculations that we discussed. Look, a linear frequency for the printed circuit board with 4 concentrated masses, theoretical prediction, analytical prediction was 142, and finite element prediction was 141, same thing. And also good agreement for the amplitudes. Also, I used other approaches that have to do, always useful, with the energy balances, because in this situation, we certainly know with high certainty the initial potential energy, and then we want to understand how this initial potential energy manifests into other energies itself, and then how we calculate that, and we obtained a very good agreement. When I based that on the energy balance, I obtained the amplitude of the linear vibrations of 47.75 millimeters, while when I use with the finite element prediction suggested 43.6, but in the previous analysis, when it was not based on the energy balance, it was 46.7. So at point is 46.7, one analytical result, 47.75, another analytical result, not bad at all, while the finite element says it's 43.6. I tell you it's not a perfect agreement, but it's a reasonably good agreement. And even finite element prediction is good, but it's, again, it's not cast in concrete. And it's also obtained using a different theory of elasticity approach, which is not supposed to result in the same data. So in other words, I want to say that finite element, we should have a lot of trust in finite element. Computer doesn't make mistakes, but it's not the results which we should consider the latest word of wisdom. It might be also an approximate result. Okay, so this is a printed circuit board with concentrated masses, and the approach based on spreading out the masses. And here also we obtained interesting results, a little bit different of the parameter of nonlinearity. You will have a chance to take a look, because I don't want to go to exactly all the results. I only try to indicate those that have to do with the physics of phenomena. Nonlinear, take a look what we did. We calculated for the pre-calculated mu, which is parameter of nonlinearity. We calculated the mu with a bar, which is dimensionless parameter of nonlinearity. Then we calculated, based on the formula that we derived and we discussed earlier, the factor of the nonlinear amplitude. And then we calculated nonlinear amplitude by multiplying the linear amplitude, which is huge, 46 millimeters unrealistically, but when we multiply it by the factor that considers the effect of nonlinearity, 0.265, the result makes sense and was confirmed by finite element analysis. The parameter of the nonlinear frequency is 747. Let's remember it. Now we'll find the nonlinear frequency itself. And the nonlinear amplitude determined the basic parameter of nonlinear frequency. That's another approach. Was 8.92. Let me tell you this: the linear amplitudes are considered, can be evaluated by dividing the initial velocity by linear frequency. Then I use a different approach. Can I evaluate the nonlinear amplitude based on the nonlinear frequency, because nonlinear frequency is significantly higher, and no wonder that the induced amplitudes will be significantly lower, and I obtained a reasonably nice prediction. That's another thing why I'm saying in nonlinear analysis, intuition, common sense, of course, I'm not saying that in other areas are not that important, but if you use the right intuition, the common sense, some non-obvious analogies, it can make your life significantly easier. Of course, it's very important that you are able to have a sanity check if you use some other analytical methods that use a little bit different assumptions, like it was an approach used on energy balance, another approach used on solving differential equation. And here we use an approach by considering an analogy between linear and nonlinear frequencies in terms of induced amplitudes, and we obtained a reasonably sane, good result. A maximum nonlinear acceleration for the nonlinear acceleration of frequency. By the way, take a look. Here, the nonlinear frequency is 696. And the parameter of nonlinear frequency is 747. Not that bad, because the the frequency of the linear frequency was only 142, right? Let me take a look what it was. If it was before, right, 142.72. Some functional dependencies that Dr. Vojošević played with for nonlinear amplitudes, how it's dependent on the number of G's. And here's also how affected about Young's modulus and the amplitude. And an interesting thing, take a look, that the Born's Young's modulus, effect of Born thickness and the amplitude, is a qualitative difference between how it affects, not only quantitative, it's clear, but also qualitative difference how the Born thickness affects linear, nonlinear amplitudes. For linear amplitudes, it's a lower plot. Its thickness has a dramatic effect right from the very beginning on the linear amplitudes, but for nonlinear amplitudes, they actually trend in the same direction because the thicker the bore, the lower the amplitudes are, but the character, the nature of these plots is absolutely different depending on whether it's linear and nonlinear response. Another thing that I mentioned a couple of times today is the role of the coordinate function in the dynamic response of a printed circuit board to impact load applied to its support contour. And we already discussed, here I'm saying, yeah, right, it's published already in Japanese Journal of Solid Mechanics and Mechanical and Materials Engineering. And the coordinate function in the dynamic response to an impact load is important to understand whether the nonlinearity, certainly we saw it, whether it affects only the principal coordinate, or we also should consider that cosine or sine might not fly, or whatever we obtain for not simply supported printed circuit boards. So that's important when we develop particularly test vehicles, and we ask ourselves whether we can, whether we want to mimic certainly non-simply support of the printed circuit board. And I want to remind you that this nonlinear response with the coordinate function, in this case, is what we did before. And we use the cosine, even in the nonlinear approach. And this is nonlinear. We still use cosine, and we obtained all these results with the cosine, nothing else. So is it sufficient to consider the nonlinear behavior of the principal coordinate because of the in-plane stresses only? Or it is necessary to account also for the effect of these stresses on the coordinate function? And I will not go through all the results. They are very complicated. They took me a lot of time. I'll simply will show the results, we'll discuss the results, and certainly the paper is published. Those who want to read it, go ahead. You can, I can send you either the paper, even the paper itself. I don't think you'll do that because, in my judgment, for you, it will be absolutely sufficient if you understand the physics and will take the results and my recommendations. So based on the developed simple and physically meaningful analytical mathematical stress model, we concluded that as far as the coordinate function is concerned, the role of the in-plane tension does not have to be considered for a simply supported printed circuit board, but has to be accounted for in the case of a clamped board. This could be done, if necessary, using the developed model. And I will simply go through a couple of numerical examples. And I will show what happened and to what extent, what are the numbers behind these statements, and why I am making these statements. So we considered a printed circuit board with the following characteristics. That's half of the length of the board, thickness, Young's modulus of the material, Poisson's ratio, distributed mass, drop height. The maximum, the highest drop height was 900 millimeters, which is about, you know, why people use 900 millimeters? Because it's approximately the height of the human chest. That's where you can more often drop the cell phone. And that's why I use 900 millimeters, but it turned out in my calculations that this height doesn't even have to be that significant. If you drop it for 20, 30 millimeters, also the result will be very, very nonlinear. Of course, with that high, significant height, it will be even more nonlinear. And I considered also situations when the coordinate function is, it should be here cosine squared. And now, okay, let's make a break, and we will continue after the break.